If you try to multiply the square roots of 3 and 12 using a calculator, you get a mess. You're multiplying 1.73205 by 3.4641, and you end up with an ugly trailing decimal that is never perfectly accurate. But if we leave those numbers in their radical forms, keeping them safely inside their root houses, we maintain perfect precision. Here is the core rule. As long as the roots are the same type, like 2 square roots or 2 cube roots, you can multiply the numbers inside directly together under a single root. So the square root of 3 times the square root of 12 combines to become the square root of 36, and that simplifies to exactly 6. No messy decimals required. Keeping numbers in their radical form guarantees clean, exact calculations from the first step to the final answer. Often, you will encounter large numbers trapped inside a root, like 5 times the cube root of 48. To simplify this, we need to factor 48 by hunting for perfect cubes. Keeping a mental list of perfect cubes, like 8, 27, and 64, makes this step much faster. Looking at 48, we can pull out an 8. So we rewrite the expression as the cube root of 8 times 6. The cube root of 8 is 2. That 2 escapes the radical and multiplies with the 5 already waiting outside, giving us a simplified answer of 10 times the cube root of 6. We can also work in reverse. Sometimes you need to move an outside coefficient inside the radical to eliminate a fraction. Take 3 times the square root of 2/3. You cannot just drag that 3 inside. To cross the boundary of a square root, it has to be squared. The 3 becomes a 9. 9 times 2/3 is 18/3, which simplifies perfectly to the square root of 6. Numbers can move freely in and out of radicals, provided you pay the toll, taking the root to exit or applying the power to enter. When adding or subtracting radicals, there is a strict condition. The terms cannot be combined unless the numbers inside the roots are exactly the same. Right now, these are completely mismatched. If we factor them down, pulling a 9 out of 45 and a 4 out of 20, we simplify the expression to 3 root 5 minus 4 root 5 plus 2 root 5. This reveals they actually share the exact same radical base. Now combine the outside coefficients. 3 minus 4 plus 2 leaves us with a single square root of 5. These rules apply directly to expanding brackets. Let's look at a common exam setup, multiplying 2 binomials containing radicals. Because these terms are identical, except for the plus and minus signs, we use the difference of 2 squares shortcut. The trap here is the first term. You must square both the 3 and the root 2. That gives us 9 times 2 minus 25. 18 minus 25 is negative 7. Radical expressions follow the exact same algebraic patterns as standard variables. Let's put these tools to work on a spatial equation. We have an isosceles trapezium. 3 of its sides measure root 63, root 175, and root 63. We know the total perimeter is root 1183. We need to find the fourth side, AD. First, simplify everything. Root 63 becomes 3 root 7. Root 175 is 5 root 7. And that massive total perimeter factors down perfectly to 13 root 7. Add the known sides together to get 11 root 7. Subtract that from the total perimeter, and our missing side, AD, is exactly 2 root 7 centimeters. Mastering radical operations allows you to solve structural problems with total precision, completely avoiding the need for rough estimates. Let's review. You can multiply numbers under the same root. You can simplify large roots by factoring out perfect squares and cubes. You can bring coefficients inside by applying the power. You can only add or subtract like terms. And you can expand binomials using standard algebra. Now it's your turn. Try simplifying this binomial expansion. 2 root 7 minus root 5 multiplied by 2 root 7 plus root 5. Work out the steps, watch out for the coefficient trap, and drop your final answer in the comments below.